Segment 3, picking up with enthalpy of phase change. We were just talking about heating and cooling curves. And so now we're going to apply our endothermic phase changes with our delta H's. So that means we must add heat. So heat is going to be energy, not just heat. Energy is going to be entering the system. So for sublimation, then delta H of sub has to be greater than 0. For vaporization, again, delta H has to be greater than 0. And then if we're melting, then delta H fusion has to be greater than 0. For our exothermic phase changes, we have to be releasing that heat. So that means energy leaving the system would be negative. And so for deposition, delta H would be less than 0. So it'd be a negative delta H sub. Delta H would have to be less than 0 for condensation, so a negative delta H of vape. And last but not least, if we're freezing, then the delta H of fusion would have to be also a negative. So phase changes then, as temperature changes, matter undergoes a phase change. That's the transformation from one phase to another. So we've talked about the equilibriums. You can have a liquid vapor equilibrium, so you have molecules in liquid. They're not in a rigid lattice, they're in constant motion. The denser than gas, so you have more collisions. Some have enough kinetic energy to escape and some won't. All right, so you take a look at the curve here for the liquid vapor equilibrium. At any given temperature, the average kinetic energy of molecules is going to be a constant. We saw that with gases. We talked about that. Same for a liquid, right? So the Ke, well, the average would be a constant. Particles do have a distribution, just like we saw in gases. Certain number of molecules then have enough Ke to escape the surface and become a gas. As we add heat, we can see that that's going to, just like we saw with gases, it's going to spread out. The average is going to go up, but there's going to be a larger distribution, except now we have a place where they can escape. So once they get to that certain point, more of them will now become a gas. So as temperature increases, so does the average kinetic energy, and so will the number of molecules with enough kinetic energy to escape. Now, vapor pressure, molecules, it's the pressure that molecules exert when they evaporate or escape into the gas phase. So the pressure of a gas when liquid or solid is at equilibrium with its gas phase. If increasing temperature will increase the vapor pressure because vaporization is endothermic. So in other words, you're going to have the liquid plus the heat of vaporization going into the gas. So equilibrium for the vapor pressure, once dynamic equilibrium is reached. Okay, so usually referred to as simply vapor pressure. So what we're saying here is that the molecules, of course, are going to be going into the gas. As they do, the pressure is going to go up in that headspace, that area above the liquid. Right? So once they do that, they go into the vapor phase. That's going to generate vapor pressure. If I increase the temperature of the liquid, then more of them are going to go into the vapor phase, which means more of them are going to contribute to the vapor pressure. So your pressure all the way around is going to go up. All right, so measuring vapor pressure. To measure pressure inside vessels, we'd use a manometer. We talked about that before. So if you want to go back and look at gases, what we can do is generate a vapor pressure diagram. So here what we can do is we can look at the variation of vapor pressure with the increase in temperature. So down here we can see temperature is going to go up, and of course the pressure starts to go up. So if we look at something like ether, it's a volatile substance. It's got a high vapor pressure near room temperature as it is, versus a propylene glycol, which is a non-volatile, which means it has a low vapor pressure near room temperature. All right, the effective volume on vapor pressure. Obviously, if you have an initial volume, and then you set up your equilibrium so that you have an existing equilibrium, as you increase the volume, the pressure will decrease. The rate of condensation then will decrease. More liquid means, more liquid will evaporate. Oh my gosh. And a new equilibrium will be established. So if we have a liquid and we set this piston to be at a certain volume, then we'll start to make our dynamic equilibrium here. And then if we pull up on the plunger, increasing the volume, decreasing the pressure, then what we're going to see is more molecules are going to go into the gaseous state and less are going to go back into the liquid state until it's reestablished in equilibrium. Now, do solids have vapor pressures? And the answer is yes, right? So at a given temperature, some solid particles have enough kinetic energy to escape into the vapor phase. When vapor particles collide with the surface, they can be captured. So equilibrium for the vapor pressure of a solid, the pressure of the vapor in equilibrium with the solid. So what we would be measuring here will be boiling points, right? So do solids have a vapor pressure? Yes. Okay, so they can. Are some of them essentially zero? Yes. My table is not going to evaporate anytime soon. Take a piece of dry ice though and put it on the table, and of course it's going to go directly into the vapor, right? So some of them will have an actual value for their vapor pressure. Now for boiling points, this is the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure. So the boiling point will increase as the strength of intermolecular forces increases, right? So when we think about water and we look at its molecular weight, its boiling point is actually quite high in comparison to other materials with the same molecular weight. So if we go to our periodic table, water is 18. You can take a look at something like methane. Methane is going to be carbon 6 plus the 4 hydrogens is 10, and it's readily a gas. If we go to, say, ethane, and we add another carbon, 2 more hydrogens, right? We're now at 18, and it's definitely a gas, whereas water is a liquid at room temperature. So that just shows you right there that that strength of the intermolecular forces is what's leading to that increase in a boiling point. So to reach what we call a normal boiling point, the vapor pressure of the liquid would be equal to 1 atmosphere. Now, the effects of hydrogen bonding, for instance. Boiling points of hydrogen compounds of elements of groups 4A, 5A, 6A, and 7A. So here, what we're looking at are your different hydrogen bonding categories, right? So if we look at just CH4, you can see it's down here. So even though it's got a high molecular weight, there's no hydrogen bonding going on in CH4, silicon tetrahydride, or germanium tetrahydride. Now, if we look at the ammonia though, you can see the ammonia travels along the line where we do have some hydrogen bonding, and you have a larger effect than what we had with methane. Same thing with HF, and H2O is way up there. So boiling points of molecules with hydrogen bonding are much higher than what we might expect. Okay, so if we're just looking at the general trend lines, we would expect water to be somewhere in here, but realistically, it's way up there. Okay, same thing with HF and ammonia. All right, which of the following will affect the boiling point of a substance? Polarizability, intermolecular forces, the external pressure on the material, all of these, or none of these? And hopefully you said all of these. Which of the following substances will have the highest boiling point? So we can look at the differences here. What are the different bonding effects we're seeing? London dispersion forces, dipole-dipole interactions, ion-dipole interactions, ionic interactions, and hopefully you came up with lithium chloride, the strongest, right? Ions. Which of the following substances will have the highest boiling point? So now here what we're looking at is completely molecular weights, right? So is the highest or the lowest going to give you the highest boiling point? And hopefully the larger molecule I2 is what you came up with. All right. So energies of phase changes, typically we express them per mole. So it's a molar heat of fusion. So delta H of fusion is by the mole. We've seen that before if you look back at your heat chapter. Heat absorbed by 1 mole of solid when it melts to give liquid at a constant temperature and pressure, right? So we have the molar heat of vaporization would be delta H vap, same thing. And of course sublimation, delta H sub. So all of these quantities tend to increase with increasing molecular force, right? And that should make sense. The more attractions we have, the more they want to stick together, the more they want to stick together, the more energy it's going to take to break them apart. How much heat in joules is required to convert 10 grams of ice at negative 10 degrees C to water at 50 degrees C? We know the specific heat of ice is 2.108, for water 4.184, and then the enthalpy of fusion is 6.010 kilojoules per mole. So how do we do this? So we have how much heat in joules is required to convert 10 grams of ice at negative 10 to water at 50. They gave us the specific heats. So if you remember, right, heat is equal to specific heat times mass times delta T. So to figure out how much heat is required, what we're going to do is take our 10 grams of ice, use its specific heat to go from negative 10 to 0. Then we're going to take the specific heat of water and go from 0 to 50. Now we just stated that changing phases is going to have an energetic effect. So we're going to add those two together for our temperature change, and then we're going to calculate how much energy went into the changing of the phase. So did it cost us energy, or did we lose energy, or did we gain energy when we convert it? That's going to be the question. So you do those three calculations, then you sum them up, and hopefully you've got 5,630. So we took 10 grams of water. Now remember, this is going to be as ice, so we're going to use the specific heat of 2.108. That gave us 210.8 joules. Then we're going to take the 10 grams of water, convert that to moles using the heat of fusion. That gave us 3,335. Now remember, we had to put that in, right? So that's going to be a positive value. Then we had 10 grams of water as a liquid at 50 degree change. That gave us 2,092 joules. We then sum them all up, and that's how we got the 5,638. Grams and Kelvin will all cancel out, then grams and mole, and then grams and Kelvin once again. All right, how much energy is required to vaporize 12 grams of ammonia if delta H of vape is 21.7 kilojoules per mole? So hopefully you can pause here, turn it back on, and you've come up with 15.29. And this was straightforward, right? You took 12 grams, got the molar mass from the periodic table, converted that to moles, then you're told 21.7 kilojoules per mole, cancel out the moles, and you get 15.29 kilojoules. All right, the next thing we're going to take a look at are phase diagrams. So it's going to be basically the illustration of all these things we've been looking at. So phase diagrams are going to show the effects of both pressure and temperature on phase change. The boundaries between phases will indicate an equilibrium. Now I mentioned the triple point earlier. The triple point is the temperature and pressure at which the solid, the liquid, and the gas are all at equilibrium together. The critical point is going to be the temperature and pressure at which a gas can no longer be condensed. Okay, so at some temperatures and pressures, it's going to remain a gas no matter what else we do. T sub C is the temperature at the critical point, and P sub C is the pressure at the critical point. So let's take a look at a phase diagram. So a phase diagram always tells us where the solid, where the liquid, and where the gas are. Now, pressure is always going to be on our y-axis, temperature on our x, and so you can see as we increase the temperature, right, we're going to become more and more likely to be a gas. If we take the pressure and turn the pressure up, we're more likely to be a solid. So x-axis temperature, y-axis pressure. As P increases, solid will be most likely, right? And that's because it's more compact. We're giving it more pressure. As T increases, the gas is going to be most likely. Of course, that's because we're giving it more energy. Now, each point equals T and P, right? So in other words, here at point B, this is our triple point, and the triple point for this material is going to be 0.01 degrees C and 4.58 torr. At point E, we get 100 degrees C and 760 torr. Okay. At point F, -10, 2.15. So we have our critical points, we have our critical temperature, our critical pressure, and then of course our triple point. So here's the phase diagram for water. So AB equals the vapor pressure curve for ice. Right, so this is your pressure curve for ice, right there. And then B to D is going to be the vapor pressure curve for liquid water. BC is your melting point line. So at any of these temperatures and pressures, that's where you're going to melt. B itself is the triple point, and then T and P, where all three phases are going to be in equilibrium. And D, of course, is your critical point. So once we reach the critical point, so at that temperature and that pressure, you have no option but now to be a gas. So in other words, once we get to this point, that's just a vertical line straight up, and you're always going to be a gas. All right, so T and P above which a liquid does not exist. All right, so case study, an ice necklace. A cube of ice may be suspended on a string simply by pressing the string into the ice cube. As the string is pressed into the ice surface, it becomes embedded into the ice. Why does this happen? So a cube of ice may be suspended on a string simply by pressing the string into the ice cube. As the string is pressed onto the ice surface, it becomes embedded into the ice. Why does that happen? Don't know that they're going to give us any answers here. All right, so I think I'll just leave that one for you. Yeah, I think I will. I was going to give you the answer, and then I thought, nah, I'll let you try to figure it out. And if you want, in fact, that's what we'll do. So for 5 bonus points, send Caro an email. We'll say 5 points in lab too. We'll make it worth something here instead of just the homework sets or whatever. An email with your explanation. Don't worry, you're allowed to be wrong. Okay, just give me your best explanation. All right, phase diagram for CO2. Now you can see the line is slanted, right? So now the line slants to the right. This is more typical, all right? Now, where is the triple point? Does that affect the triple point, or is the triple point still where all three of these lines meet? That's your answer, right? How about the critical points? Where are the critical points? Did that affect it? Nope, critical point's still right up here. All right, so what should you expect for a test question here then? Well, if I were going to give you a test question based on phase diagrams, which I will, typically I give you the phase diagram, tell you what the material is, and then ask you questions about where is the triple point? What's the pressure of the triple point? What's the temperature of the triple point? What is the pressure of the critical point? What is the pressure, or what is the temperature of the critical point? Things of that nature, right? Or I'll give you actual set of data and say, at this temperature, 200 Kelvin, and this pressure, 1.5 atmospheres, what phase will this material be in? Right? So you need to be able to read the graph and give the phase, or tell me where the different points are, or both. Right? So that's what you should be prepared for these types of questions. All right, supercritical fluids. These are substances with temperatures above its critical temperature and a density near its liquid density. They have unique properties that make them excellent solvents. So values of the critical temperature tend to increase with increased intermolecular interactions between particles. So it's just following exactly what we'd expect of a boiling point, right? All right, Le Chatelier's principle. So if you've never heard of Le Chatelier's principle, equilibrium are often disturbed or upset. So whenever we have a dynamic equilibrium of a system and we do something to upset it, then what we say is that the system will correct, okay? So the system responds in direction that tends to counteract the disturbance. If possible, it will try to restore the equilibrium. So if I have a system at equilibrium and I disturb the system will react to reestablish that new equilibrium. So position of the equilibrium then is used to refer to relative amounts of substances on each side of the arrows. So in other words, we'll have our double-headed arrows. So I might say something like a liquid plus heat, gives us a vapor, and the arrows will be in equilibrium, so they're going both ways. Now what I'm going to do is I'm going to increase the temperature. So I'm going to take my equilibrium and I'm going to disturb it. What's going to happen? Well, if I increase the temperature, that means I'm adding heat. So now what I can think of is this being on a rope, right? So if it's on a rope and I push or pull, maybe a rope's not the best idea, maybe a pole, if you will. But if I push on the system, then the system is going to go to the right. If I pull from the right, then it's going to go right. If I pull from the left, it's going to go left. So if I pull heat out and I start to put cool in, then it's going to go back over to liquid. Right? If I put heat in, then it's going to push it over to the vapor. So we're going to increase the amount of vapor here, which will decrease the amount of liquid. At that point, we say the equilibrium has shifted, and we say it's shifted to the right because it went to the product side. More vapor is now produced at the expense of the liquid. Temperature-pressure relationships can be represented using a phase diagram. Okay, so we can look at that relationship on a phase diagram. So at 89 degrees C and 760 millimeters of mercury, what physical state is present? Solid, liquid, gas, supercritical fluid. Not enough information is given. So here's our temperature in degrees C. So we'll find 89. It's right about here. Then 760, right about there. And so we can see we have a liquid. Okay. Now if I change and add heat, what's going to happen? Well, if I add heat, it's simply going to shift along the line until it becomes a gas. All right, so measuring the delta H of vaporization. We have the Clausius-Clapeyron equation. All right, so measure pressure at various temperatures, and then you can plot it. So we'll take the natural log of P, and it's going to be equal to that delta H of vaporization divided by R divided by T plus degrees C, right? So, or excuse me, plus, I think that's a constant. So it's 2-point form of the Clausius-Clapeyron equation. Measure pressure at two temperatures and solve the equation. Wouldn't expect to do this. Let's see, the vapor pressure of diethyl ether is 401 millimeters of mercury at 18 degrees C. Its molar heat of vaporization is 26 kilojoules per mole. Calculates vapor pressure at 32 degrees C. So again, this would be plug and chug. Wouldn't expect too much of this to be on your test though. We have a lot of bonding to be on this next exam. So that's what you probably want to be prepared for. Hopefully you can run that through your calculator though, and you can come up with that. Right? And they give us a U return, determine the enthalpy of vaporization. So now you're just going to solve for delta H of VAP. So again, you can work on those. You can look over the solutions. I'm not going to spend a lot of time on it because, as I said, I wouldn't expect that to be on your test. All right, types of solids, crystalline solids. Oh, actually, I think we'll pause here. It's a great place to stop right after the year turns. So we'll pick up probably be our last segment will be on types of solids and getting into the crystalline 3D lattices, lattices. So we'll take a look at those next. All right, stay tuned for that one.